Hello, my name's Amanda Liu, and I'll be discussing our work on a framework for verified tensor program optimization via high-level scheduling rewrites. When we're talking about high-performance computing domains such as image processing and deep learning, programs often take the form of computationally intensive algorithms over multidimensional arrays. Although these algorithms can mostly be declaratively expressed as pure mathematical expressions, there's in fact a whole spectrum of possible code realizations or schedules for computing a single algorithm. Optimizing these programs boils down to interleaving computation on arrays through using different arrangements of nested loops. These schedules span a large trade-off space with greatly differing memory and compute properties. For instance, an algorithm can be separated into various stages where each intermediary stage is computed and stored in full. We can collapse any of these stages into the next to immediately merge the computation and get rid of any persistent intermediary values. Or, instead of computing each stage in its entirety before proceeding to the next, we can compute smaller chunks or tiles at a single time iteratively. We can vary the sizes of these tiles or vary the stages over which we do this, or vary the looping order that determines which elements are computed when. All this to say, there's a lot of possible schedules for a given algorithm, and all of these factors of loop ordering, locality, and compute granularity can all greatly impact performance. Writing fast array programs comes down to optimizing schedules in this trade-off space. However, manually navigating such a wide variety of schedules, not to mention with the full force of their imperative details, can be an unwieldy, error-prone task. Instead, it would be nice to navigate this trade-off space with, first, a level of functional abstraction. Writing large loop nest structures with complex index arithmetic can be quite difficult. It would be easier to talk about programs at a higher level of abstraction than direct imperative code. It's no secret that many of these algorithms we're concerned with in high-performance computing lend themselves well to a pure functional representation. A simple look at recent work developing functional array languages such as Futhark and Dex speaks to the merit of this approach. And so it would make sense to follow suit and not only express our programs at this level of abstraction, but optimize them, source to source, at this level too. We'd also like a degree of well-defined imperative control at a high level. It's nice to have functional abstraction to protect us from having to deal directly with imperative code. However, in order to produce highly efficient code and perform all the kinds of transformations we just talked about before, we still need a way to describe scheduling decisions that affect low-level code that aren't naturally exposed at the functional level. Moreover, we would like to do so still without having to reason about any imperative code explicitly. And finally, we would like formal guarantees. So as we're transforming a schedule to optimize it, we would like some formal assurances that we're not changing the semantics of the algorithm. In other words, we'd like for our optimizations to be formally verified. With these goals in mind, we developed a framework for navigating the space of schedules and optimizing tensor programs in a principled, formally assured manner through a series of verified rewrites on a high-level functional tensor language. Our framework contains an extensible set of Coq theorems that we call scheduling rewrites that are modular statements of equivalence, often conditional, between two programs. We also provide a powerful set of tactics that automates away proof details such as any preconditions for the scheduling rewrites applied. This allows the programmer to reschedule their program in a high-level proof script that applies a sequence of scheduling rewrites and reads at the level of abstract details similar to that of a mathematical proof. And finally, we provide a trusted low-rank process that compiles our functional language into C and is used for benchmarking purposes. To provide the degree of imperative control we named as a goal before, we introduce into our source language a set of reshape operators that are defined in the source language and perform array operations such as concatenate and transpose. These operators can be unfolded into their program definitions or be left intact and act as compilation directives that induce the corresponding low-level changes to the generated imperative code. We have preliminary results on a set of representative examples that show that our framework is able to produce efficient code on par with that produced by state-of-the-art systems with weaker formal guarantees, like Halide. Moreover, we show that our framework has greater scheduling expressivity. We're able to schedule a family of useful program transformations beyond what is even reachable in Halide. Thank you, and if you'd like to hear more about our work, we hope to see you at POPL 2022.